Hi, everybody. So sorry that I couldn't make it to class today. I'm going to be out of town attending to some family stuff. But I didn't want to just cancel class, so I figured I'd make a quick video essentially doing what I would have done had we had class today. So I know it's not ideal, but hopefully it's better than nothing. It was either this or get somebody else in there. But I kind of thought that having another teacher in there with sort of a different style, not really knowing how we run things, might be more of a disruption than it is a help for you guys. So my hope is that you prefer a video like this to actually meeting in person this week with somebody else. I should be back in town late this weekend, so I will be in class next week as normal. Anyways, before I get into the specific homework assignment that's due tonight, which is 7.1, I guess I should write that down. What I want to do is kind of go over a few announcements. So homework 7.1 is due tonight, and then as always, I know I don't even need to write this. You probably know at this point. You have a quiz. It covers 6.3. I don't know why it's so hard for me to write. And 7.1. And that quiz, just as a reminder, is due tomorrow, assuming you're watching this on Thursday. Maybe I should write the days instead of the tonight things, because who knows when you'll watch these. So there we go. I guess that's a little bit more specific. And then, as always, the corrections due on Saturday. So as far as announcements go, hopefully you got an email from me. I don't want to say yesterday anymore. On Tuesday, I think is when I sent it. Shortly, I don't know, early afternoon. That had a spreadsheet in there showing your midterm grade and where you stand in the class. So hopefully you got that. If you didn't get that, just reach out to me and I can resend it or send it to you. But it's good information to have, and it's a good time to check in and make sure that you have grades for everything that you've done. For example, there's certainly people who have taken quizzes but then didn't do the corrections, or corrections didn't upload correctly or something. And I put little comments in the grade book, but sometimes students don't see those, and so you end up with a zero on something you shouldn't get a zero on. So if you're in that boat, definitely let me know. I want to get those all fixed for you. As far as more pressing matters, we got a quiz on Friday. It covers 6.3 and 7.1. I think last class I talked kind of about what will be on there from 6.3. But just so that you have it again, there's really three different types of questions. And rather than kind of describe them, maybe I'll give you examples, and that'll be enough for you to figure out what I'm talking about. They all deal with inverse trig functions. The first type is when I just ask you something like the arc sine or the arc cosine or the arc tangent of some memorized value on your unit circle. So you're like, what, like pi over 6 or something? No, I'm not giving you an angle. When we talk about an arc sine function, you give me the angle. I'm giving you, if it's arc sine, a memorized y coordinate on your unit circle. So for example, I don't know, negative 1/2. And what you need to do is figure out where on your unit circle does the sine of an angle equal negative 1/2. In other words, where on your unit circle is the y coordinate equal to negative 1/2? You might be like, that's a trick question. There's lots of different places. True, but arc sine should always be a value between negative pi over 2 and positive pi over 2. So maybe you're thinking this value over here, which I think ends up being, what, negative pi over 6? Hopefully I'm not screwing anything up in front of you. That's the first type of question. So to be clear, this is the question, and this is the answer. The second type is very similar, except now we compose together trig and inverse trig functions. And that's not just because it kind of makes for a fun little brain teaser type question. It's because there actually are some applications for composing together trig and inverse trig functions in future math classes. In our class, we don't do a whole lot with it, but it is useful later on. So the second type is when your inverse trig function is on the outside. So I don't know, like arc tangent maybe. Sure, that'll work. Arc tangent of what? Instead of just a memorized point on your unit circle, so like root 3 or root 3 over 3 or something, it would be a trig function. So let's see if I can come up with a good one. I could make it like I want the answer to be 1, and the sine of pi over 2 is 1. I think that's all right. I think this works out to be a decent little example. Right, I can ask you for the arctangent of the sine of pi over 2. And so what you do is you figure out the sine of pi over 2, and the sine of pi over 2 is just some number. So again, here's the question. And what your answer would be, or what it would look like, is maybe something like, first you'd figure out the sine of pi over 2. You're like, pi over 2, I'm thinking up here. The y coordinate up here is 1. So the sine of pi over 2 is 1. So he's just asking you what's the arctangent of 1. And now all of a sudden question 2 looks a lot like question 1. Right? If you can get this far, then it turns into a type 1 question, which presumably you can finish. So this is not done. This is not the answer. The answer would go over here, but maybe you can get it from there. Arctangent is looking for a value on the right side of your unit circle, so between negative pi over 2 and positive pi over 2. And it's looking for an angle, and it wants an angle so that the tangent of that angle is equal to 1. So maybe you're thinking, sure, I'll switch color somewhat arbitrarily. This point up here, maybe you're thinking pi over 4. If you are, that'd be fantastic. That'd be the answer to this question. Finally, the third type of question. What's going on here is you again have composed trig and inverse trig functions. I don't know why I'm drawing the box first. But they're composed in the other order. So instead of the arctangent of the sine of something, maybe it's the sine of the arctangent of something. Sure, that works. And that something can be a memorized value off of your unit circle. So like the number 1, for example. Or that can correspond with a fraction that's not a memorized value off your unit circle. So maybe it's better to practice in case it's not. So a number like 2/3 or something. This is not a memorized value off your unit circle. And for this one, maybe think you're going to do the substitution method. So let t equal the arctangent of 2/3, and then kind of go from there. So hopefully that makes sense. If it doesn't make sense, you can go back and look at the videos from last time. But anyways, this is all the 6.3 stuff. Really, the purpose of today was supposed to be the 7.1 stuff. It's a new chapter, chapter 7, so it might not surprise you to hear that it's not all that related to what we did in chapter 6. What chapter 7 is all about, it's called analytic trig, but the idea is it's kind of where algebra meets trig. And that might sound terrible to you, but it's really not that bad. In fact, I kind of like it. I think 7.1 is kind of fun. What you need to know for 7.1 is we've been thinking, so maybe in the past, you've been thinking about the sine of some angle being the y-coordinate on the unit circle, the cosine of an angle being the x-coordinate, the tangent of an angle being the y divided by the x, the cosecant of an angle being 1 over y, the secant, you're like, yeah, I get the point, you can stop. I can't stop. Gone this far. I'm going to continue. There's t's in here. The cotangent of an angle being x over y, right? This is what we've been thinking about for defining our sine, cosine, tangent, cosecant, secant, and cotangent functions. And when I write x over y, or y over x, or 1 over x, when I write x's and y's, I'm referring to x and y coordinates on your unit circle. Right? That's what we've done in the past. Now, kind of in chapter 7, what we're going to do is kind of take this same idea, but recognize that if the sine is the y and the cosine is the x, and then everything else is just some fraction of x's and y's, we don't have to write tangent as y over x, because y is the sine, right? And x is the cosine. So what we could do is we could say, all right, sine of t is a thing, and cosine of t is a thing, but then tangent of t, instead of thinking about that as y over x, we could write that in terms of sine and cosine. Right? Because sine is the y, cosine is the x, so if tangent is y over x, tangent is sine over cosine. Right? Kind of cut out the middleman, cut out the x's and y's, and just substitute things in. Instead of thinking about cosecant as 1 over y, you could think about cosecant as 1 over sine, because the sine is the y. And secant of t you could think of as 1 over cosine of t. And cotangent of t you could think of as cosine of t over sine of t. And you're like, all right, I guess I could do that. I'm not sure why. Well, the reason you'd want to do that is it allows you to simplify trig expressions. So think some big jumble. Oh, that sucks. These didn't form out well. Maybe I can do something about that. Think I'm going to have to fix this. Think some big mess. I mean, I know you can't see this, but what this really should say is 1 plus cosine over y over 1 plus secant of y. That's what this is really saying. It just didn't render properly when I printed this out so I could write on it. Some big mess of trig expressions. This simplifies really nicely. In fact, this simplifies all the way down to either a single trig function, so think like tangent or secant or something, or a constant, like the number 1 or the number 2. Like, really? How? Like, do you cancel out the ones? No. There's going to be a lot of algebra involved in simplifying this thing. But that algebra that you'll do to simplify this thing will be dependent upon all these different identities. I mean, in short, what we're going to do is we're going to change everything that's not a sine or a cosine into a sine and cosine. So like up here, where I have 1 plus cosine over 1 plus secant, cosine's already sine or cosine, but secant's not. right? Secant is the same as 1 over cosine. So I can rewrite this expression this way. And it doesn't look like I'm simplifying, right? This looks a lot worse than this. But by rewriting everything in terms of sines and cosines and then doing a bunch of algebraic tricks, and that's the step where you might struggle a little bit, I'll be able to simplify this really nicely. And this will simplify really nice all the way down to a single trig function or a constant. And I'll give you lots of examples. Like really, the only way to learn 7.1 is to do a bunch of examples, which is why you have all this homework. But they all kind of turn out the same, right? You do the same steps. Step 1 is you rewrite everything, all your trig functions, in terms of sine and cosine. So loosely speaking, get rid of all of the tangents, cosecants, secants, and cotangents. And really, I guess I should write sine of t and cosine of t. I should write whatever the variable is. Often it's t, but in this case, the variable was y. Don't confuse that y with this y. They're completely different. They're just choosing to use the letter y as the variable for my angle. Rewrite everything in terms of sines and cosines. And then step 2, and this is kind of a loaded step 2, is simplify. Because this could be a huge mess. This could be super hard. How do you simplify? Well, you use everything you know about algebra. Right? Sometimes you end up with fractions inside fractions. So you multiply by the reciprocal of the denominator. Sometimes you can factor out like a sign from the numerator and the denominator, and you can cancel those out. Right? You simplify using all the methods that you have to simplify. The good news about this simplification step is that's not true. It mostly involves algebra you already know. And when I say you, I mean that kind of depends. There's different levels of algebraic comfort in this class. But in theory, you've seen all of the simplification steps that you'll be doing in step 2 here in previous classes, with one exception. The one exception is, when I say in the past, we can write sine, cosine, tangent, cosecant, secant, and cotangent in terms of x's and y's. We also had this kind of nice relationship, right? X squared plus y squared equals 1. This is the equation of the unit circle. It says that any point on the unit circle, the square of the x coordinate plus the square of the y coordinate has to be equal to 1. It has to be. But look, if the cosine is the x coordinate and the sine is the y coordinate, then not only can I rewrite tangent, cosecant, secant, and cotangent in terms of sine and cosine, I can rewrite this identity in terms of sine and cosine. Instead of thinking about this equation as x squared plus y squared equals 1, I can think about it as cosine squared plus sine squared is equal to 1. And this will allow me lots of simplification. So when I simplify, I'll be using tricks I already knew and this fact. This is what's called the Pythagorean identity, and it'll probably be the trickiest part for you in terms of the simplification that you do. So there's a quick summary of kind of what you're doing. Really, you shouldn't learn things these way from this quick summary. Hopefully you've watched all the different videos, and this is all a quick review for you, and that's really useful. But there's the quick summary of what we're doing in Chapter 7. What you should expect to see on your quiz from Chapter 7 are, well, Chapter 7 problems are kind of predictable, right? They'll look just like homework. Meaning, I'm going to give you some mess of trig expressions, right? So think something that looks like this, for example. And what you're going to do is simplify it. And the term simplify is kind of loaded. So what I'm going to tell you is to simplify it so that it's either a constant or a single trig function. Meaning your answer can't be something like cosine over sine, because that's 2 trig functions. But your answer could be cotangent, because that's a single trig function. So I'll write these problems really carefully so that they simplify. The method you'll use to simplify will be the same methods that you use in the homework. So I know sometimes homework, all the problems are a little bit different. This time they're not. They're all kind of the same. You're given an expression and you simplify it. The only thing that can differ is the level of difficulty in that simplification. In the homework, you'll see different levels of difficulty, and on the quiz, you'll see different levels of difficulty, and the quiz will be based upon the problems you do in the homework, just like it always is. So that's what you should expect to see from 7.1 quiz. It'll look just like these homework problems. Without further ado, let's get to the homework problems. All right, through the magic of editing, what I've done is I've gone in, I've rewritten all these problems that didn't render properly. So what's written in these various colors is how it should show up, or at least similar to how it should show up when you actually go into the homework. And the good news is the first few did render just fine, so I didn't have to rewrite all of them. I think what you'll find when you go through this homework assignment is there's kind of an increasing level of difficulty as we go through. So maybe I'll work out a couple of the easier ones, a couple of the medium ones, a couple of the harder ones, and we'll call this good. So this first one here, if you have no idea how to get started on a problem like this, your first step can always be the same. And note I said can, because a big challenge of 7.1 is there's different ways you can do these problems. You don't have to do them the way that I suggest, but the way that I suggest will work. And I think it's the easiest way to do it, but you don't have to do it that way. If your level of your algebraic comfort is really, really high, and you see other ways that might be easier for you, feel free, right? I just try to pick a way that is the most predictable and the easiest for students who maybe aren't quite as comfortable with algebra and don't have the confidence of just looking at something and figuring out. Anyways, without further ado, secant times cotangent. What I would do first is I say secant, that's not sine or cosine, but I can rewrite that in terms of sine and cosine. Secant is the same as 1 over cosine. So the secant of t is the same as 1 over cosine of t. And I'm taking that and I'm multiplying it by cotangent. And cotangent, that's not sine over cosine either. Sorry, that's not sine or cosine either. But that can be rewritten in terms of sine and cosine. Right? The cotangent is the same as the cosine divided by the sine. So step 1, rewrite every trig function, 2 in this case, in terms of sines and cosines. And that's this little cheat sheet that I wrote for you down here. All right, what do we have? The secant is 1 over cosine and the cotangent is cosine over sine. I think those are the two that showed up here. Yeah. All right, so we get here. But we're not done at this stage. Right now we're on to step 2, which is simplify. And how do you simplify this? Well, if you're comfortable with simplification, you might recognize that since we have multiplication here, this cosine in the denominator here can cancel with this cosine in the numerator, because I don't have to put the line through it. And if those cancel out, I'm left with just 1 over sine of t. And you're like, oh, cool, that's my answer, 1 over sine of t? No, because it's not a constant or a single trig function. It's 1 divided by a single trig function. Fortunately, you can rewrite 1 over sine of t as cosecant of t. All right, so we kind of first go from other trig functions into sines and cosines, then we simplify, and then sometimes that simplified answer needs to be switched back into our sort of other trig functions. Cosecant of t would be your answer here. Note that typically the variable is t, but it's not always t, so be careful. Like down here, if this simplifies to sine of t, and you put in sine of t, it'll mark it incorrect because your variable here is an x. But in this case, it was a t, so the answer is cosecant of t. Is it worth doing this one? Sure, why not? Get you off on a good... No, I'm not. I think you can do this on your own. Nope, I'm going to do it for you. Secant is not sine or cosine. It's 1 over cosine. Some people, when you're lazy, you leave it just like that. This has no meanings. Like COS doesn't mean anything in math. It'd be like if you wrote square root. You're like, what is 3 plus square root? Someone look at you like, what are you talking about? Oh, 3 plus the square root of 4, right? Square root is a function that needs an argument. Just like cosine is a function that needs an argument. Cosine of pi or something. Right? So you can't just leave cosine by itself without an argument, but a lot of people do. Really, what you should write is cosine of t, because that's your variable here. Secant, same as 1 over cosine of t. Tangent is the same as sine over cosine. Again, there's me being lazy. It's the same as sine of t over cosine of t. So I get a fraction divided by a fraction. Hey, haven't we seen that already in this class? Maybe you're thinking. Yeah. Well, you divide fractions, you multiply by the reciprocal of the denominator. All right, so I take this one that's down on the bottom, I flip it upside down, that gets me here. Hey, this looks a hell of a lot like this. Well, it's the exact same, huh? That's kind of coincidence that's the exact same. All right, cosine on the top and the bottom, that can cancel out. So I got 1 over sine. 1 over sine is the same as cosecant. Looks like my answer down here is also cosecant. No, all your answers won't be cosecant. Just coincidentally, they are for these first two. All right, so that's not so bad. Like, all right, I kind of get the hang of it. Maybe you could try that on question 3 or question 4 or even question 5. I don't think any of these are all that bad. Yeah, they're squared now, but that's fine. No big deal. Things will cancel out pretty nicely. I think you'll be able to figure out what these are equal to. Maybe they end up being a constant in these, if I remember right. If I'm doing this in my head right. Or maybe not. I don't know. I shouldn't make that assumption. 1 over cosine. Yeah, I think they are. I think a lot of stuff can't... When I say constant, I mean a number. Like maybe the number 1 ends up being the answer there. So maybe you can kind of mess with 3 and 4 and 5, and stuff should simplify. They should be a lot like 1 and 2. They look worse, but they're really not any harder than 1 and 2 end up being. Same with 6. It's not anywhere. I mean, there's more terms. More stuff will cancel. But that cancellation step, it's kind of satisfying. Like, everyone loves doing that, right? Even when you can't do that, people love doing that. You'll do a lot of that on these problems. And that's what kind of makes chapter 7.1, I don't know, satisfying, for lack of a better word. But then things change a little bit when you get to question 7. So I would say the first 6 are all of kind of the same type. You write them in sines and cosines. They kind of look like fractions. You cancel out. You get your answer. You're done. Question 7 is the first one that will kind of feel a little different to you. And note that I put this in here. What's going to happen on a lot of these are square roots and squares are going to cancel out. But really, square roots and squares don't cancel out. I don't know if I even want to get into this. I guess I've gone this far. If you have the square root of x squared, a lot of people think that that's x, but it's not. It's actually the absolute value of x. You can't just cancel out square roots and squares, even though people do it all the time. If you're canceling out the square root and the square, you're assuming that x is positive. But x might not be positive, right? Think about the square root of negative 2 squared. Well, negative 2 squared is positive 4. So this is the square root of positive 4. And the square root of positive 4 is positive 2. So if negative 2 is in here, the square and the square root don't just cancel out. The negative 2 turns into a positive 2. It's not true that squares and square roots just cancel out. Technically, you have to put in the absolute value symbols. Nobody ever does. And if you're going to not do it, you must be assuming that x is a positive number. So what I added on here, this wasn't in here before I changed this problem, is you can assume that t is in quadrant 1. So squares and square roots do cancel. Because if you're in quadrant 1, then everything is positive. Sines are positive, cosines are positive. So you don't have to worry about this weird case where negative 2's turn into positive 2's, loosely speaking. For your purposes, ignore this technical note. And if you end up with something like, I don't know, sine squared t and square root, know that you can just make that sine of t. You don't have to make that the absolute value of the sine of t. Anyways, that little rant aside, that's not what makes this problem harder. What makes this problem a little bit harder is you end up using the Pythagorean identity. You're like, oh yeah, I remember that. You talked about that at the start of the video. That's the one where sine squared t plus cosine squared t is equal to 1, right? Yep. You're like, all right, so first I'm going to look at everything and change it into sines and cosines. Done. It's already all sines and cosines. Now I'm going to try to simplify this. I'll cancel out these. No, you won't. You cannot cancel out these because we have 2 terms up on the top. Because of this minus sign, these don't cancel. You're like, all right, but I'll cancel out these. Nope. Can't cancel out those either, again, because we have multiple terms up top because of this minus sign here. You're like, all right, fine. I'll cancel out the square root and this square, and I don't know, maybe this square, and I don't know, make this the square root of 1, or I don't know what the hell you do. You can't do that either. Or you can't distribute exponents over multiple terms because we have 2 terms up top here. None of that cancellation works. Just doesn't. All right, so stop telling me what I can't do. Why don't you tell me what I can do? What you can do is use the Pythagorean identity. You're like, okay, so where's the sine squared plus cosine squared that I'm going to change into 1? I don't see a sine squared plus cosine squared anywhere in here. It's not in here. But what you can do is you can rewrite your Pythagorean identity. Because look what happens if you take this and subtract cosine squared from both sides. Then on the left, you'd have sine squared t. And on the right, you'd have 1 minus cosine squared t. This is an alternative form of the Pythagorean identity. And it's really useful to be able to recognize alternative forms of the Pythagorean identity. In this specific case, I got 1 minus cosine squared t here in the numerator. And this alternative form of the Pythagorean identity tells me that 1 minus cosine squared t is the same as sine squared t. So this is equal to the square root of sine squared t divided by cosine squared t. Here you got lots of options for what you do. One option is to change the square root of this fraction into the fraction of these square roots. You're like, whoa, you're kind of distributing that. I thought you said that you couldn't distribute square roots to multiple different terms. You can't. But these aren't multiple different terms because I don't have any plus or minus signs going on here. So I can take this square root and distribute it to the top and the bottom. Very common mistake. People try to make the square root on the 1 and then another square root on the cosine squared. You can't do that. But you can do this. And the advantage of doing this is I have the square root of sine squared, which is just sine. I have the square root of cosine squared, which is just cosine. And sine divided by cosine is just tangent. So this answer ends up just being tangent of t. Note that you could have at this step said sine over cosine is the same as tangent. So sine squared over cosine squared is the same as tangent squared. And now I got the square root of something squared. So those cancel out, and I get the tangent of t. Technically, they don't cancel out. Technically, you get absolute value symbols here, But what I said is you don't need the absolute value symbol, so you can just put tangent t as your answer. A little bit more difficult, I guess, because you have to use this Pythagorean identity. Question 8 will look like this. These are hard. There's several of this type. I think 8 and 9 and 10 all kind of end up working the same. So maybe I'll just do one of them. I already started 9. I guess I can go back to that one. Right, it starts out, I know that it doesn't look this way. It'll render like this. 1 plus cosine of y is my variable. Y, I don't know y, divided by 1 plus secant of y. So my first step is to take anything that's not a sine or a cosine and change it into a sine or a cosine. So secant, I'll change that into 1 over cosine. But now I got this mess. What in the world I'm going to do with this mess? Well, if it were, you got fractions inside fractions. If it were just one fraction divided by one fraction, you could flip things upside down, but it's not. But we can make it that way. The top is 1 plus cosine of y. I can divide that whole thing by 1, and now it looks like a fraction. Right? Something divided by 1. On the bottom, I got these two different fractions, but this one, I can view it as cosine of y over cosine of y, right? 1 is the same as 1 over 1, which is the same as cosine of y over cosine of y. This is just 1. It's a different form of 1, but it's a really useful form of 1, because now I got a common denominator down here in the denominator. Guess I'll go this way now, sure. How is that useful? Well, look what happens. I got 1 plus cosine of y over 1, and then down in the bottom here, if I have the same denominator, I can add up the numerators. At cosine of y plus 1. If you're really clever, you might notice, or even if you're not really clever, you might notice that 1 plus cosine of y and cosine of y plus 1 is the exact same thing. I can rewrite this. I don't even know where these arrows are going. Down here now, maybe? Sure. As 1 plus cosine of y over 1. Instead of divided by all this stuff, I'll make it times the reciprocal of this stuff. So times the cosine of y divided by, and then I could write cosine of y plus 1. Or maybe it's more clear if I write 1 plus cosine of y. Same thing, right? Cosine of y plus 1 and 1 plus cosine of y is the exact same. 5 plus 4 is the same as 4 plus 5. But by writing it this way, I have this and this that can cancel. You're like, no. You told me that you can't cancel when you have multiple terms because of this plus. True. I can't cancel just the cosine. If there's a I can't cancel this cosine and this cosine. Can't do that because of this plus sign. But because this entire thing is the same as this entire thing, I can cancel these. And I'm left with cosine of y over 1. In other words, cosine of y. This started way the hell up here. This answer would end up being cosine of y. Is that where it started? Yeah, I think that's where it started. Question 10 is a lot like question 9. Right? I mean, you can almost see it, right? Question 8 is even more similar. Right? This format looks almost identical to this. Change everything into sine and cosine. Maybe you'll have some fractions inside fractions. Maybe look for common denominators like we did here. Flip things and cancel them. It should work out really nicely. Nice thing about this section is you know if you're right or wrong, kind of. Right, if things just blow up and your answer is sine cubed minus cosine squared plus 7 or something, like, nah, something went very, very wrong. These should simplify really nicely either to a constant or a single trig function. So give this one a try, kind of in the same method of question 9. And I think even though 10 looks a little bit different, I think 10 ends up playing a lot like 8 and 9. So do the same thing here. Change them into sines and cosines, make it a fraction over fraction, flip and cancel. Question 11, I don't know if that's worth doing. I mean, we can if you want. The method's the exact same. I'm asking somebody. I'm not going to bother with 11. No one's going to watch this whole video. That's not true. Hopefully everybody watches this whole video. But the longer I make it, the less likely it is people are going to stick around. I think you can do 11. Ones that are different are 12, just fundamentally different. 13, and then these last two, 15 and 16. So let's at least start those. This one, I think this is how this renders. Right? Is this fraction minus the number 1 all underneath the radical. I think that that's correct if I have all my parentheses in the right spot. We'll see. Maybe I'll work through this entire problem. So what would you do if you saw a problem like this? Well, first off, this is really hard. Right now we're getting into the, on the quiz that I usually try to do an easier one, a medium one, and a harder one. Easier one, we're talking like one of the first 7. One of the first 6, sorry. Medium one, we're talking about like 7 or 8 or 9 or 10 or 11. Really hard one, we're talking about 12 or 13 or 14. And then 15 and 16, I think they're kind of fun. Harder than anything you'd see on your quiz. I guess it could be an extra credit question at some point, although I don't think it ever will be. Anyways, back up to question 12 here. What would you do here? Well, it's overwhelming. You don't know where to start. What do you do when you don't know where to start? Change everything into sine and cosine. It's going to be a mess. I guess blue, right? I mean, maybe we'll run into this blue down here, but fine. Square root of a huge mess. Up top, I have the number 2 plus tangent squared. But tangent is sine over cosine. So it's sine over cosine squared. My variable is the letter x here, it looks like. I could square this entire thing. Or I could be like the square of a fraction is the square of the top divided by the square of the bottom. So tangent squared is the same as sine squared over cosine squared. What about secant squared? Well, secant is 1 over cosine. So secant squared is 1 squared over cosine squared. But 1 squared is just 1. So you can write it like this. I got this minus 1. Got options. I think what I would probably do, I don't know if this is true, that this is really what I do, but I think that what most students would probably do is they'd be like, well, it's not a fraction over a fraction, but if it were, I'd be a lot more comfortable. Why don't I think about this 2 right here as 2 over 1? So that I can then think about it as 2 cosine squared over cosine squared. So that then I have the same denominator here. Maybe you can see all those steps. Think about what you'd end up with. If this is 2 cosine squared over cosine squared, I'd have 2 cosine squared plus sine squared divided by cosine squared. I got the same denominator here and here if this is cosine squared. So I can just write that denominator once. I'm going to divide that whole thing by 1 over cosine squared. I got that minus 1. You're like, oh, awesome, cosine squared, you guys are gone. Nope, dumb work, because you got plus sign here. And sorry for harping so much on like what doesn't work, but I just know from experience that's what everyone tries to do. I can preemptively help out there. You're like, all right, I can't do that, but look at this. Cosine squared plus sine squared, I'm just going to change all that into a 1. That'll make things work out really nicely. Nope, can't do that either. Because you don't have cosine squared plus sine squared. You got 2 cosine squared plus sine squared. You could write this 2 cosine squared as cosine squared plus cosine squared, and then you'd be able to get rid of part of it using that Pythagorean identity. If you're thinking that, that'll work. I think there's an easier way. And I think what most students would probably do is they'd be like, well, I did all this work to make it a fraction over a fraction. Why don't I take advantage of that? I got the square root of 2, I'm going to need more square root, cosine squared x plus sine squared x divided by cosine squared x. And then instead of dividing that by this thing, why don't I multiply it by the reciprocal of that thing? Right? All this fraction looking thing turns into this. And then don't forget, you still have this minus 1, which is underneath the radical. It's like right there, just hanging out, waiting for later. The reason you might think to do that is because now you got this cosine and this cosine squared that can cancel. These ones cannot. These ones absolutely can. If you do that cancellation, you get the square root of, let's see, if this is gone and this is gone, all I'm left with is this, minus 1. So I got 2 cosine squared x plus sine squared x minus 1. Square root of that. Square root, cool. Square root squares cancel maybe? No, they absolutely do not. Because you got this plus and minus. Because you have multiple terms. You cannot distribute square roots over multiple terms. So what do? You got a Pythagorean identity hidden in here. Actually, there's a couple different ways you can do it. I think the way I would do it is recognize that there's a Pythagorean identity right there. Generally, when you have differences of sine squareds and cosine squareds and 1s, sine squareds or cosine squareds and 1s, you can use your Pythagorean identity. So like, all right, I bet this is something. I don't know what it is, but I bet it's something. We'll come back up here where we wrote our Pythagorean identity and think about how can you rearrange the terms in this original thing so that you end up with sine squared x minus 1. Well, if I subtracted 1 from both sides and subtracted cosine squared from both sides, on this side I'd have sine squared t minus 1. And on this side, I'd have negative cosine squared t, right? This goes to this side, this goes to this side. So sine squared t minus 1 equals negative cosine squared t. So sine squared x minus 1 equals negative cosine squared x. So instead of writing something, this, sine squared x minus 1, I can write negative cosine squared x. So I got 2 cosine squared x plus negative cosine squared x. So what I got here, I got 2 of these cosine squared x things minus 1 of these cosine squared x things. So I just got 1 of these cosine squared x things. Right, 2 minus 1 is 1. The square root of cosine squared is cosine of x. Technically, you have absolute value symbols, but I'm telling you, you can ignore all that. This ends up being the answer, the cosine of x. This is really hard. Right, if you can follow this level of algebra, you have algebraic skills beyond what most students do when they enter a calculus class. And if you don't be too hard on yourself. Just kind of go through and try to follow all the different steps. And if you're thinking about different stuff, talk to me. Like, could I have done this? Could I have done this? I try to emphasize the things you can't do, but there's definitely other things you could do. Anyways, that's question 12. I think questions 13 and 14 are doable if I give you some hints. So let me give you some hints. For this one, maybe I should do it in blue, but I've already used so much blue, it's going to be pink. Think FOIL. All right, I got these parentheses. It'd be nice if they weren't there. Multiply this times this, this times this, this times this, this times this. All right, what you'll get is a sum of 4 things. Something plus something plus something plus something. And those things will have all sorts of trig functions in them. Cosines, cotangents, cosecants. Change all those into sines and cosines. Stuff should cancel out fairly nicely. You might have to use your Pythagorean identity, and it'll simplify. So I think, there's different ways you can do this, but I think the way that's probably most straightforward is think FOIL first, then change everything into sines and cosines. You can do it in either order. It's just easier that way. What about this one here? I don't know why this is so late. I don't think this one is especially hard. I think that you can handle this one. Change it into sines and cosines, get a common denominator, look for your Pythagorean identity. I think it should simplify fairly nicely. I think. I kind of want to work it out because I think it's, now that I'm looking at it, I think it's going to end up being like cosine squared. So now I'm all confused because look, tangent, I'll just do it super quick, right? Because I'm worried that it's not right and I have to like get rid of it for you or something. Tangent is sine squared over cosine squared. And secant is 1 over cosine squared. Oh, how convenient. Oh, these are x's and not t's. Fine. I know you don't care, but I care. Sine squared x over cosine squared x is the same as tangent squared x. And from that, I'm subtracting secant, which is 1 over cosine squared x. I got a common denominator. That's cool. I can rewrite this as sine squared. Oh, maybe this does work out. Always trust the homework. Sine squared x minus 1 over cosine squared x. Maybe you can use Pythagorean identity here. And maybe that'll allow you to cancel. And maybe you'll end up as a constant as your answer over here. So I was afraid it didn't work, but it does work. So I don't know, ignore the last minute of this video, or that video. Ignore what I just said. This one works out fine. You can do it. It's not super hard. It should be much earlier in the assignment. 15 and 16 are kind of weird. They're just ways for you to do more algebra. You can do them in any way you want. But essentially what's going on in 15 and 16 is the prompt is a little bit different. Instead of saying simplify it so that you get a constant or a single trig function, it's saying simplify it so it looks like this. So it's something over cosine. And then tell me what that something is. That's weird. Okay, you got 2 options, right? Either you can just multiply the cosine to the other side and say f of x, the thing that my answer will be, right? Maybe answer, f of x, it doesn't matter. F of x is equal to cosine of x times tangent of x plus secant of x. And then simplify. Right, you simplify this just like you've been doing. Right, simplify, you get your answer goes right here. It's probably the most straightforward way to do this. Another way to do it is mess with the left-hand side. Right, change this into sines and cosines, this into sines and cosines. mess with the left-hand side until it's something over cosine of x. So your goal is a little bit different. Your goal is not just to simplify the left-hand side, it's to mess with the left-hand side so that it's something over cosine. And when you get it to be something over cosine, something becomes your answer. So it's up to you. Either you can multiply the cosine to the other side of the equation and simplify the entire mess. That'll get you the right answer. Probably easier. Or you can be like, fine, I accept your challenge. You want me to rewrite this in this strange form as something over cosine? Sure, I'm so good with algebra that I can do that. And then the thing that is the something, not the entire fraction, but the thing that's the something will be your answer over here. You do that twice. It's the exact same thing here. Right? This all simplifies into f of x over sine of x. It's up to you whether you want to just mess with this side of the equation until it looks like this. That'd be pretty damn hard. Might be able to do it. Some of you guys are really good at this stuff. I bet some of you could. I don't know that you want to. Another option is just multiply sine to the other side. Or if you multiply the sine of x over to the other side, you get sine squared x over cosine of x minus cosine cubed x. And then try to simplify that. Hint, when you're trying to simplify that, right, if this is gone and this goes here, is cosine of x minus cosine cubed x is the same as cosine of x times 1 minus cosine squared x. Wait, what just happened there? These both have a cosine in them, so I factored out that cosine. If I factor a cosine out from cosine, I'm left with just a 1. If I factor a cosine out from cosine cubed, I'm left with cosine squared. If you recognize that there's a cosine that you can factor out from the denominator, then maybe you can use your Pythagorean identity on this, and that'll help you simplify some stuff. So there's your little hint for this one. I think you can deal with these. 15 and 16 are a little bit weird. Great if you can get them. Don't stress if you can't. As far as your quiz, expect them to look more like the earlier problems on the homework. And I think I didn't look at your quiz as carefully as I should, but my guess is there's probably 3 problems on there. And I bet one of them is roughly, I don't know, question 2-ish. And I bet the second one is roughly, I don't know, question 8-ish. And then the last one is roughly, I don't know, question 12-ish. Right. And if you can do those, you should be in good shape for your quiz. So that's all I got. Hope you guys have a good weekend. Feel free to send me an email if you need anything from me. I'll be taking care of some stuff, but I'll have access, so try to help you as much as I can. All right, that's all. Bye.